Picture yourself standing alone in a natural history museum as the last echoes of closing announcements fade into silence. The vast halls stretch before you, filled with the reconstructed skeletons of creatures that once ruled our world. Before you towers the magnificent frame of a Tyrannosaurus rex, its fossilized bones catching the dim emergency, lighting in a dance of shadows and ancient mysteries. You stand there, dwarfed not just by its size, but by the incomprehensible weight of time it represents. 66 million years since this apex predator last drew breath. But here, in this moment of quiet contemplation, we must ask ourselves a question that challenges everything we think we know about the story of life on Earth. What if this magnificent creature, this king of the dinosaurs, was not among the earliest chapters of complex life's grand narrative, but rather a relatively recent addition to a story that had already been unfolding for eons beyond our imagination? The dinosaurs dominated our planet for approximately 165 million years, a span so vast that the human mind struggles to grasp its true meaning. To put this in perspective, if the entire history of human civilization were compressed into a single day, the age of dinosaurs would stretch across more than 3 years. Yet even this monumentally long era represents only a small fraction of Earth's deeper history. Before the first dinosaur ever hatched from its egg, our planet had already been spinning through space for over 4 billion years, a duration 25 times longer than the entire age of dinosaurs. Consider this staggering fact. The time that separated the first dinosaurs from the emergence of complex life during the Cambrian explosion was longer than the time that separates us from those first dinosaurs. During those hundreds of millions of years before dinosaurs, life was not idle. The fossil record reveals a world teeming with innovation, experimentation, and increasingly sophisticated forms of organization. Vast reefs built by ancient corals stretched across primordial seas. Forests of towering tree ferns created the first terrestrial ecosystems. Life had already mastered photosynthesis, developed complex cellular structures, and even survived multiple mass extinctions that rival the one that ended the dinosaurs' reign. This is where our journey begins, not with the familiar story of the dinosaurs, but with the vast, largely unexplored territories of deep time that preceded them. We stand at the threshold of a question that has profound implications for how we understand intelligence, consciousness, and our own place in the cosmic story. If life had hundreds of millions of years to experiment with forms of organization we can barely imagine, if the conditions on early Earth were so radically different that they might have favored evolutionary pathways completely foreign to our experience, what are the mathematical odds that intelligence, complex, organized, perhaps even technological intelligence, never emerged during those unimaginably long eons? The scientific method teaches us to base our understanding on evidence, yet it also encourages us to ask bold questions and follow them wherever they might lead. Tonight, we embark on a journey through deep time, guided by both rigorous scientific inquiry and the kind of expansive thinking that has led to humanity's greatest discoveries. We will examine geological formations that suggest possibilities our textbooks never considered, explore mathematical probabilities that challenge our assumptions about the rarity of intelligence, and investigate cutting-edge theories from quantum physics that might preserve echoes of civilizations so ancient that they predate the very face of our planet as we know it. The story we are about to unfold is speculative, but it is speculation grounded in real science, in actual discoveries, in patterns that emerge when we step back and look at the vast canvas of Earth's history with fresh eyes. Whether or not ancient civilizations actually existed before the dinosaurs, the very act of asking this question opens doorways to understanding that can transform how we see ourselves, our planet, and our place in the universe's ongoing story of consciousness awakening to itself. So let us begin this journey together, leaving behind the familiar landscapes of recorded history and venturing into territories where time moves differently, where the impossible becomes merely improbable, And where the silence of the deep past might still be whispering secrets, we are only now learning how to hear. The vast canvas of forgotten time. When we attempt to comprehend the true scale of Earth's pre-dinosaur history, we encounter one of the fundamental limitations of human consciousness: our inability to truly grasp deep time. Our minds, evolved to navigate the rhythms of days and seasons, the span of human lifetimes, struggle helplessly when confronted with the vast eons that preceded the age of dinosaurs. Yet it is precisely this incomprehensible vastness that opens the door to possibilities we have barely begun to explore. To understand what we're contemplating, we must first expand our perception of time itself. The Precambrian era, that vast stretch of Earth's history before complex life forms left clear fossil records, encompasses nearly 4 billion years. This is not merely a large number. It represents a duration so immense that it defies meaningful comparison. If we were to represent all of Earth's history as a single year, the entire age of dinosaurs would occupy only the month of December, while human civilization would flash by in the final minutes before midnight on New Year's Eve. The Precambrian would fill the first 10.5 months of this cosmic year, a canvas of time so vast that entire evolutionary experiments could rise, flourish, and vanish without leaving traces we could easily recognize. During this seemingly endless expanse of deep time, our planet was anything but static. The geological record reveals a world in constant transformation, where continents formed and broke apart, where atmospheres changed their very composition, where life itself underwent revolutionary transformations that would shape the trajectory of existence for eons to come. The Great Oxidation Event, occurring around 24 billion years ago, fundamentally altered the chemistry of our planet's atmosphere and oceans, creating conditions that would eventually allow for complex multicellular life. This single transformation took place over hundreds of millions of years, itself a span longer than the entire age of dinosaurs. Consider the stromatolites, those layered rock structures created by ancient microbial communities that we can still observe today in places like Shark Bay, Australia. These formations represent some of the earliest evidence of organized, cooperative life on Earth, dating back over 3.5 billion years. Here we see life not merely surviving, but creating complex, structured communities that modified their environment on a massive scale. These ancient microorganisms didn't simply exist. They engineered their surroundings, creating the first examples of biological architecture on our planet. The Cambrian explosion, that remarkable burst of evolutionary innovation that occurred around 540 million years ago, represents what many consider the beginning of complex life as we know it. Yet this event, dramatic as it was, occurred after 3.5 billion years of evolutionary experimentation. When we truly absorb this timeline, we begin to realize that the Cambrian explosion was not the beginning of life's complexity, but perhaps its first clear signature in the fossil record, the first chapter we can easily read in a story that had already been unfolding for eons. Modern radiometric dating techniques, using the predictable decay of radioactive isotopes, allow us to measure these ancient timeframes with remarkable precision. These methods reveal layer upon layer of geological history, each stratum telling its own story of environmental change, biological innovation, and planetary transformation. Within these layers, scientists have discovered evidence of sophisticated chemical processes, complex mineral formations, and even what appear to be the remains of ancient organic structures that challenge our understanding of when complex organization first emerged. The more we study these ancient time periods, the more we realize how much we don't know. The rock record from the earliest eons of Earth's history is fragmentary, altered by billions of years of geological processes. Yet even these incomplete traces reveal glimpses of a world far more dynamic and complex than we once imagined. We find evidence of early life forms that developed sophisticated chemical processes, created complex community structures, and even survived catastrophic events that would have seemed unsurvivable. What strikes researchers most profoundly about these discoveries is not just the age of complex organization on Earth, but the speed with which it appears to have developed once conditions allowed. Life didn't gradually stumble toward complexity over billions of years. Instead, whenever opportunities arose, it seemed to leap toward increasingly sophisticated forms of organization with what can only be described as remarkable efficiency. This pattern of rapid organizational innovation, repeated again and again throughout the geological record, suggests that intelligence and complexity are not rare accidents in the universe, but perhaps fundamental tendencies of matter and energy when given sufficient time and opportunity. The implications of this vast temporal canvas are staggering. If we accept that intelligence and complex organization are natural tendencies of evolving systems, and if we acknowledge that Earth provided nearly 4 billion years for such systems to develop before the first dinosaur appeared, then we must seriously consider the mathematical probability that some form of advanced organization, perhaps even what we might recognize as intelligence, emerged during those unimaginably long epochs. If life found ways to organize and create complex structures billions of years before dinosaurs, what other forms of organization might have emerged in those unimaginably long epochs? When Earth was an alien world, to truly appreciate the possibility of pre-dinosaur intelligence, we must journey back to experience Earth as it once was, not the familiar blue-green world of our imagination, but an alien planet whose conditions were so radically different from today that they might have favored evolutionary pathways completely foreign to our carbon and oxygen-based perspective. This ancient Earth was not merely a younger version of our current world. It was effectively a different planet entirely, with atmospheric compositions, climate patterns, and environmental conditions that would be utterly unrecognizable to modern life. Imagine breathing air that contained almost no oxygen but was rich with methane, hydrogen sulfide, and ammonia, compounds that would be instantly lethal to modern complex life, yet which might have provided the perfect chemical foundation for entirely different forms of organization and intelligence. During Earth's earliest eons, the atmosphere was a reducing environment, fundamentally different from the oxidizing atmosphere we know today. This wasn't simply a hostile environment for modern life. It was an environment that would have promoted entirely different chemical reactions, different metabolic pathways, and potentially different forms of information processing and organization. The transformation from this methane-rich early atmosphere to our oxygen-dominated modern atmosphere represents one of the most dramatic environmental changes in our planet's history. This shift, largely driven by the photosynthetic activities of ancient cyanobacteria, took place over hundreds of millions of years and fundamentally altered every aspect of our planet's chemistry. For life forms that had evolved in the earlier reducing environment, this gradual oxygenation would have represented a slow-motion apocalypse, forcing either adaptation to radically new conditions or extinction. Yet for new forms of life that could harness oxygen's reactive power, this atmospheric transformation opened entirely new possibilities for energy production and complex organization. Perhaps even more dramatic were the periods scientists call snowball Earth episodes, when our entire planet may have been covered in ice from pole to pole. During these eras, which occurred multiple times in Earth's deep history, surface temperatures plummeted so severely that oceans froze solid, creating a world that would have been virtually unrecognizable. Yet life not only survived these planetary deep freezes, it may have used them as opportunities for evolutionary innovation. Beneath the ice, in the crushing darkness of frozen oceans, life forms would have been forced to develop entirely new survival strategies, potentially including forms of organization and information processing that we can barely imagine. The formation and breakup of supercontinents also created environmental conditions that have no modern parallel. When vast landmasses like the ancient supercontinent Rodinia came together, they created continental interiors with climates more extreme than anything we experience today. The center of these supercontinents would have experienced temperature variations, seasonal patterns, and atmospheric conditions that could have selected for forms of life adapted to extremes that dwarf our modern extremophiles. As these supercontinents broke apart, they created new ocean basins, altered global circulation patterns, and established entirely new ecological niches. During certain periods in Earth's ancient history, atmospheric oxygen levels reached concentrations of 35% or higher, nearly twice the current level. This oxygen-rich environment would have fundamentally altered the metabolism and behavior of any complex life forms that existed at the time. Higher oxygen concentrations enable more efficient energy production, potentially allowing for larger body sizes, more active lifestyles, and more energy-intensive processes like complex computation or information processing. Some researchers speculate that such high oxygen environments might have provided the energy foundation necessary for advanced forms of biological intelligence. Even Earth's physical properties were different in the deep past. Our planet's rotation was faster, creating shorter days and stronger Coriolis effects that would have influenced weather patterns, ocean currents, and atmospheric dynamics in ways that might have favored different evolutionary strategies. The moon was closer, creating more dramatic tides that would have repeatedly exposed and submerged vast coastal areas, creating unique environments for life forms that could exploit these regular transitions between aquatic and terrestrial conditions. The gravitational environment itself may have been subtly different due to changes in Earth's internal structure and the distribution of mass within the planet. These variations in gravitational fields, while small by astronomical standards, could have influenced the development of early life forms in ways we are only beginning to understand. Some theoretical biologists suggest that slight variations in gravitational conditions might favor different forms of cellular organization, different structural solutions to the challenges of maintaining complex biological architecture. What makes these ancient environmental conditions particularly intriguing from the perspective of possible ancient intelligence is their extreme stability over geological timescales. While individual environmental conditions were often harsh by modern standards, they remained relatively constant for millions or even hundreds of millions of years. This kind of long-term environmental stability would have provided exactly the conditions necessary for complex evolutionary experiments, enough time for sophisticated adaptations to develop, enough consistency for complex systems to refine themselves, enough predictability for advanced forms of organization to emerge and persist. Modern astrobiology has taught us that life can thrive in conditions we once considered impossible, in the crushing depths of ocean trenches, in the acidic hot springs of volcanic regions, in the radiation-bathed environments around nuclear reactors, even in the vacuum of space itself. If life can adapt to such extreme conditions in the relatively short time available on modern Earth, what kinds of adaptations might have been possible given hundreds of millions of years in environments that were stable, if alien by our standards? The fossil record from these ancient periods is necessarily incomplete. The processes that preserve fossils work differently under different atmospheric and chemical conditions. But what little evidence we do have suggests that life was not merely surviving in these alien environments, but experimenting with forms of organization that left subtle traces in the geological record. Some of these traces suggest large-scale coordination among early life forms, sophisticated chemical communication systems, and even what appear to be primitive forms of environmental engineering. In these alien conditions, what if intelligence evolved along pathways so foreign to our carbon-based, oxygen-breathing perspective that we wouldn't even recognize their traces? The archaeology of the impossible. The question of what evidence ancient civilizations might leave across geological timescales forces us to confront one of the most humbling realizations in all of science. How little of our current existence would survive to tell future archaeologists our story? This sobering reflection becomes the key to understanding what traces of pre-dinosaur intelligence we might realistically expect to find, and more importantly, what unusual evidence we should be looking for in the most ancient rocks on Earth. Consider this thought experiment. Imagine that human civilization suddenly vanished today, and future geologists attempted to reconstruct our existence after 100 million years of geological processes had worked to erase our traces. What would remain? Our greatest cities would have crumbled to dust, their materials recycled through countless cycles of erosion and deposition. Our plastics, those seemingly permanent markers of industrial civilization, would have long since broken down into unrecognizable chemical signatures. Even our nuclear weapons and power plants would leave only the faintest isotopic whispers in the geological record, subtle anomalies that might be attributed to natural processes by researchers who had no context for understanding their true origin. Yet even as this exercise reveals the impermanence of obvious civilizational markers, it also points toward the kinds of traces that might actually survive across such vast timescales. Certain materials and structures, when preserved under specific geological conditions, can persist for billions of years. The key is understanding what kinds of evidence to look for and where to find it. Enter the Klerksdorp spheres, discovered in South Africa's Wonderstone silver mine in rocks dating to approximately 3 billion years ago. These small, spherical objects, with their distinctive grooved patterns, have puzzled geologists since their discovery. While mainstream science explains them as concretions formed by natural geological processes, their remarkably uniform size, perfectly spherical shape, and intricate surface patterns have led some researchers to wonder whether they might represent something more intriguing. The mathematical precision of their construction, the consistent spacing of their surface grooves, and their occurrence in specific geological formations create a pattern that stretches the boundaries of what we typically expect from purely natural processes. Even more intriguing is the Oklo Natural Nuclear Reactor in Gabon, Africa, where uranium deposits apparently achieved sustained nuclear fission reactions approximately 2 billion years ago. Mainstream geology explains this as a remarkable but natural phenomenon, where specific geological conditions concentrated uranium to the point where it spontaneously achieved critical mass. Yet the precision required for such reactions to occur naturally and to continue in a controlled manner for hundreds of thousands of years suggests a level of organization and control that challenges our understanding of what natural processes can accomplish without guidance. These examples point to a crucial insight. The evidence for ancient intelligence might not look like what we expect. We search for pyramids and roads, for tools and buildings, because these are the markers of our own civilization. But intelligence that evolved under radically different environmental conditions, with access to geological timescales for its development, might leave signatures that we would initially interpret as natural phenomena. Modern taphonomy, the scientific study of how organisms and their traces become preserved in the fossil record, reveals that preservation across geological time is an extraordinarily rare and specific process. The vast majority of all organisms that have ever lived left no trace whatsoever in the fossil record. Even large, numerous species with hard parts like shells or bones have preservation rates of less than 1% across geological time. For soft-bodied organisms, or for artificial structures that might degrade more rapidly than biological materials, the preservation rate approaches zero. This sobering reality forces us to reconsider what we might realistically expect to find. If an advanced civilization had existed hundreds of millions of years ago, its traces would need to be either extraordinarily durable or preserved under exceptional circumstances to survive to the present day. This leads us to look not for obvious artifacts, but for subtle anomalies, unusual isotope ratios, unexpected mineral formations, geometric patterns in ancient rock layers that suggest organization rather than random natural processes. Recent advances in materials science have identified several classes of structures that could theoretically survive billions of years under the right conditions. Diamond, with its incredibly stable carbon lattice structure, could preserve information indefinitely if protected from extreme heat and chemical attack. Certain crystalline structures, particularly those formed at high pressures and temperatures, create what amount to natural time capsules that could theoretically preserve evidence of ancient processes for geological timescales. More intriguingly, some researchers have proposed that advanced civilizations might have learned to encode information directly into the quantum structure of matter itself. While this remains highly speculative, quantum information theory suggests that certain types of information, once encoded into the fundamental structure of materials, might persist across timescales that dwarf conventional preservation mechanisms. The study of what our own civilization might leave behind reveals another crucial insight. The most durable traces of technological civilization are often its unintended consequences rather than its intended monuments. The subtle changes we've made to atmospheric chemistry, the alterations we've created in isotope ratios through nuclear technology, the synthetic compounds we've created that have no natural analogs. These invisible signatures might persist long after all our buildings and machines have crumbled to dust. This perspective leads us to examine ancient rock formations, not just for obvious artifacts, but for subtle anomalies that might represent the unintended consequences of ancient technological processes. Unusual concentrations of rare earth elements, unexpected isotope ratios in ancient minerals, chemical signatures that suggest large-scale industrial processes. These might be the actual archaeology of impossible civilizations. Perhaps most challenging to our conventional thinking is the possibility that ancient intelligence might have operated on scales and timescales so different from our own that their engineering projects would be indistinguishable from natural geological processes. If a civilization had millions of years to develop and thousands of generations to refine their techniques, they might have learned to work with geological forces rather than against them, creating modifications to planetary systems that would appear to us as natural phenomena. The theoretical physicist Freeman Dyson once proposed that truly advanced civilizations might reorganize entire star systems to harness energy more efficiently. Following this logic to its natural conclusion, ancient terrestrial civilizations might have learned to reorganize geological systems, atmospheric compositions, or even the fundamental chemistry of their environment in ways that would appear to modern observers as natural evolutionary processes. If we can barely detect traces of human civilization from just 10,000 years ago, what whispers of intelligence might be hidden in rocks that are millions of times older? The mathematics of hidden histories. When we approach the question of pre-dinosaur intelligence from a purely mathematical perspective, we encounter probabilities that challenge our most fundamental assumptions about the rarity of consciousness in the universe. By applying the same statistical reasoning that scientists use to estimate the likelihood of extraterrestrial intelligence, but focusing on terrestrial deep time rather than galactic space, we discover that the odds of intelligence having emerged only once in Earth's 4 billion-year history may be far smaller than we have traditionally assumed. The Drake equation, formulated by astronomer Frank Drake to estimate the number of active, communicating extraterrestrial civilizations in our galaxy, provides a framework we can adapt to examine the probability of ancient terrestrial intelligence. While Drake's original equation considers factors like star formation rates and the likelihood of planets developing life, We can modify these parameters to examine the likelihood of intelligence emerging during the vast timescales available in Earth's pre-dinosaur history. Consider the fundamental variables. Earth has existed for approximately 4–6 billion years, with conditions suitable for complex life for roughly 4 billion of those years. During this immense span, life has demonstrated remarkable consistency in developing increasingly sophisticated forms of organization whenever environmental conditions permit. The transition from simple prokaryotic cells to complex eukaryotic cells occurred relatively quickly in geological terms. The development of multicellular organization followed a similar pattern of rapid innovation once the basic building blocks were in place. Recent research by astronomers Gavin Schmidt and Adam Frank, published in the journal Astrobiology, explores what they call the Silurian hypothesis, the question of whether we would be able to detect evidence of ancient industrial civilizations in the geological record. Their mathematical analysis reveals that even a civilization lasting hundreds of thousands of years might leave only the most subtle traces in rock layers, and that multiple such civilizations could have risen and fallen without leaving clear evidence that we would recognize with current detection methods. The mathematics become even more intriguing when we consider the concept of convergent evolution, the tendency for similar solutions to emerge independently in response to similar environmental challenges. Intelligence, defined as the ability to process information, solve problems, and adapt behavior based on experience, has evolved independently multiple times in Earth's recorded history. We see it in vertebrates like dolphins and primates, in cephalopods like octopi, in social insects like ants and bees, and even in some plants that demonstrate sophisticated information processing capabilities. If intelligence emerges this readily in the relatively short timescale we can observe directly, the mathematical probability that it never emerged during the vastly longer timescales of deep time becomes vanishingly small. Using conservative estimates for the rate of evolutionary innovation and the time required for complex intelligence to develop, statisticians calculate that Earth has had sufficient time for hundreds or even thousands of independent experiments in complex intelligence during the pre-dinosaur era. Information theory provides another mathematical framework for understanding these possibilities. Claude Shannon's work on information transmission and storage reveals that any system capable of complex organization must be able to process, store, and transmit information efficiently. The fossil record shows us that even early life forms developed sophisticated information processing capabilities. Genetic codes that rival modern computer systems in their elegance and efficiency, cellular communication networks that coordinate behavior across vast scales, and even primitive forms of environmental sensing and response that demonstrate basic learning capabilities. When we calculate the information processing capabilities of early biological systems, we discover that the basic building blocks of intelligence were in place billions of years ago. Early cellular networks were already capable of distributed information processing, environmental sensing, adaptive response, and even primitive forms of memory storage. From a mathematical perspective, the leap from these early information processing systems to more sophisticated forms of intelligence represents an extension of existing capabilities rather than a fundamental innovation. The concept of exponential growth in complexity also supports the mathematical case for ancient intelligence. Once a system reaches a certain threshold of information processing capability, improvements tend to accelerate rapidly. We see this pattern in our own technological development, where advances in computing power, artificial intelligence, and information processing have followed exponential rather than linear growth curves. If similar processes occurred in ancient biological systems, the time required to develop sophisticated intelligence might be far shorter than we traditionally assume. Statistical analysis of evolutionary innovations reveals another compelling pattern. Major evolutionary breakthroughs tend to occur in clusters, with periods of rapid innovation followed by longer periods of gradual refinement. This pattern, observed consistently throughout the fossil record, suggests that when environmental conditions favor innovation, evolutionary systems respond with remarkable speed and creativity. Given the vast timescales available in Earth's deep history, and the multiple environmental transitions that would have created opportunities for innovation, the mathematical probability of repeated intelligence emergence becomes quite high. Perhaps most significantly, recent research in complexity theory demonstrates that intelligence and consciousness may be emergent properties of any sufficiently complex information processing system. Rather than being rare accidents requiring specific environmental conditions, intelligence may be an inevitable outcome whenever matter and energy organize themselves into sufficiently sophisticated patterns. If this theoretical framework is correct, then intelligence is not a rare exception in the universe, but a fundamental characteristic of complex systems given sufficient time and resources to develop. The mathematics of hidden histories also must account for what statisticians call the detection problem, the likelihood that we would actually recognize evidence of ancient intelligence even if it existed. If we assign conservative probabilities to our ability to detect, interpret, and correctly identify subtle traces of ancient technological activity, the mathematical models suggest that multiple ancient civilizations could have existed without leaving evidence that we would currently recognize or correctly interpret. When we combine all these mathematical factors, the vast timescales available, the demonstrated tendency of evolutionary systems toward increasing complexity, the multiple independent emergence of intelligence in recorded history, and our limited ability to detect ancient technological signatures, the statistical case for pre-dinosaur intelligence becomes surprisingly robust. The mathematics suggest that the absence of obvious evidence for ancient civilizations may tell us more about the limitations of our detection methods than about the actual probability of such civilizations having existed. If the universe tends toward complexity and organization, and Earth had billions of years to experiment, what are the mathematical odds that intelligence emerged only once? Echoes in stone and gene. Deep within the molecular structure of every living cell lies a library more ancient and comprehensive than any archive humanity has ever created. Our genetic code, that elegant double helix of DNA that carries the instructions for all biological complexity, may be far more than a simple blueprint for proteins and cellular machinery. Recent discoveries in molecular biology and information theory suggest that our genes might actually preserve encoded messages from civilizations so ancient that they existed before our planet's face was recognizable, their wisdom written into the very foundation of life itself. To understand how this might be possible, we must first appreciate the remarkable stability and information storage capacity of genetic systems. DNA, despite its delicate appearance, represents one of the most durable information storage systems ever discovered. Under the right conditions, genetic material can preserve information for millions of years, far longer than any human storage technology. But more intriguingly, the genetic code appears to contain far more information than is necessary for its basic biological functions, leading some researchers to wonder whether portions of our genome might serve as repositories for information that has nothing to do with immediate survival needs. The concept of so-called junk DNA, those portions of the genome that don't seem to code for proteins or serve obvious biological functions, has been largely abandoned as scientists discover that these regions often contain sophisticated regulatory systems, complex information processing networks, and patterns that suggest purposes we don't yet understand. Some theoretical biologists now propose that these regions might actually be libraries of information preserved from earlier evolutionary periods, genetic fossils that carry messages from ancient biological systems. Recent advances in bioinformatics have revealed that genetic codes show evidence of mathematical structures far more sophisticated than random mutation and selection would predict. The genetic code appears to be optimized not just for protein synthesis, but for error correction, information compression, and even what appear to be redundancy systems designed to preserve information across evolutionary time. These characteristics suggest that genetic systems might have been shaped by intelligence, not necessarily divine intelligence, but perhaps by ancient biological intelligences that learned to encode information directly into the foundation of life itself. Crystalline structures in ancient geological formations provide another potential repository for information from the deep past. Crystals, with their highly ordered atomic arrangements, can preserve information for geological timescales under the right conditions. Some minerals form complex three-dimensional patterns that could theoretically encode vast amounts of data, creating what amount to natural hard drives embedded in the Earth's crust. While most such formations are assumed to result from purely natural processes, some exhibit patterns of organization that push the boundaries of what we expect from random crystallization. The study of mineral formations in some of Earth's oldest rock layers has revealed structures that appear to exhibit what information theorists call non-random organization, patterns that are too regular, too complex, or too purposeful to result easily from purely natural processes. Some ancient quartz formations show internal structures that resemble the kind of three-dimensional matrices that modern computer scientists use for advanced data storage. While these could certainly result from unusual but natural geological processes, they could also represent attempts by ancient intelligences to create permanent repositories of information using the most stable materials available to them. Geological formations themselves might preserve evidence of large-scale environmental modification by ancient intelligences. Certain mountain ranges exhibit mathematical properties, ratios, angles, and spacing patterns that seem too regular to result from random tectonic forces. Some ancient crater formations show evidence of modification after their initial formation, suggesting that they might have been used as natural amphitheaters or communication, arrays by intelligences that learn to work with rather than against geological forces. Underground cave systems present another intriguing possibility for preserved information. Some ancient cave networks exhibit organizational patterns that suggest purposeful construction or modification. These systems often show evidence of sophisticated engineering, air circulation patterns, acoustic properties, and structural reinforcements that seem to exceed what natural processes would create. While most can be explained by conventional geology, some exhibit features that challenge our understanding of what natural cave formation can accomplish. Perhaps most intriguingly, some researchers have proposed that ancient intelligences might have learned to encode information directly into the quantum structure of matter itself. Quantum information theory suggests that information encoded at the quantum level could theoretically persist for geological timescales under specific conditions. While this remains highly speculative, recent advances in quantum computing and quantum information storage have demonstrated that it is theoretically possible to encode vast amounts of data into the quantum states of crystalline matrices. The concept of morphic fields, proposed by biologist Rupert Sheldrake, suggests that information about biological forms and behaviors might be preserved in subtle field effects that influence future development. While controversial and not accepted by mainstream science, this theory provides a framework for understanding how information about ancient biological systems might influence modern life in ways we don't yet fully understand. If morphic fields exist, they could serve as a kind of biological internet, connecting modern life forms to information networks established by ancient intelligences. Indigenous wisdom traditions from around the world contain remarkably consistent stories about ancient civilizations, advanced technologies, and sophisticated understanding of astronomical and geological processes. While these traditions are often dismissed as mythology, some researchers note that they preserve technical knowledge that seems to exceed what we would expect from cultures without written records or advanced instruments. The consistency of these traditions across widely separated cultures suggests that they might preserve genuine historical memories passed down through oral traditions across vast timescales. Recent discoveries in epigenetics, the study of how environmental factors influence gene expression, have revealed that experiences and environmental conditions can actually modify genetic expression in ways that can be passed down to future generations. This mechanism provides a theoretical pathway by which information about ancient environmental conditions, technological processes, or even cultural knowledge could be preserved in genetic systems and transmitted across evolutionary time. The implications are profound. If our genetic code, our planet's geological formations, and even our cultural traditions carry encoded information from ancient intelligences, then we are not merely the products of random evolutionary processes, but the inheritors of vast libraries of ancient wisdom. Our drives toward technological advancement, our intuitive understanding of mathematical relationships, our deep emotional connections to natural patterns, all of these might represent not learned behaviors, but inherited memories from civilizations that learned to encode their knowledge into the very foundations of matter and life. Could the very building blocks of life carry encrypted messages from civilizations so ancient that they existed before our planet's face was recognizable? The cycle keepers. Among the most puzzling aspects of Earth's behavior are the remarkably regular cycles that govern its climate, magnetic field, and geological processes. While we have learned to predict these cycles and even depend upon their consistency, their underlying regularity challenges our understanding of what natural systems can accomplish without guidance. What if some of Earth's most fundamental rhythms are not natural phenomena at all, but the legacy of ancient intelligence that learned to work with planetary systems on timescales that dwarf human comprehension? Consider the ice ages, those dramatic climate cycles that have shaped Earth's environment for millions of years. These cycles follow patterns of remarkable mathematical precision, with glacial and interglacial periods recurring according to orbital cycles known as Milankovitch cycles. While astronomers can explain these cycles in terms of regular variations in Earth's orbit, axial tilt, and wobble, the precise timing and consistency of ice age cycles suggests a level of systematic organization that seems almost too elegant to result from purely random interactions between orbital mechanics and climate systems. What makes these cycles particularly intriguing is their apparent fine-tuning for biological diversity and evolutionary innovation. Ice ages don't simply create harsh conditions that threaten life. They create precisely the kind of environmental variability that drives evolutionary adaptation and speciation. The regular alternation between glacial and interglacial conditions creates expanding and contracting refugia for species, genetic bottlenecks that drive rapid evolution, and new ecological niches that favor innovation and adaptation. From the perspective of promoting biological complexity and diversity, ice age cycles function as if they were designed by an intelligence that understood the evolutionary process and sought to optimize it for maximum creativity and innovation. Earth's magnetic field presents another puzzle of seemingly engineered regularity. The geomagnetic field reverses its polarity at intervals that show statistical patterns suggestive of underlying organization, though the exact timing appears random on shorter timescales. These reversals serve crucial functions for life on Earth. They help redistribute radiation, influence atmospheric chemistry, and even affect evolutionary processes by creating periods of increased mutation rates that can drive speciation. The magnetic field acts as a planetary shield protecting life from harmful cosmic radiation, but its periodic reversals also create windows of opportunity for evolutionary innovation. The carbon cycle, that vast system of carbon exchange between atmosphere, oceans, land, and living organisms, displays a level of self-regulation that has maintained conditions suitable for complex life across geological timescales, despite massive perturbations from volcanic activity, asteroid impacts, and other catastrophic events. This system's ability to maintain homeostasis across billions of years suggests what systems theorists call intelligent design characteristics, not necessarily divine design, but the kind of sophisticated feedback systems that usually result from purposeful engineering rather than random processes. James Lovelock's Gaia hypothesis proposes that Earth itself functions as a kind of superorganism, with all its biological and geological systems working together to maintain conditions suitable for life. While this hypothesis is often interpreted metaphorically, recent research in systems theory and complexity science suggests that planetary-scale self-regulation of the kind Lovelock describes typically emerges in systems that have experienced some form of guidance or programming. Complex systems rarely develop such sophisticated homeostatic mechanisms spontaneously. They usually require what engineers call intelligent initialization to establish the feedback loops necessary for stable self-regulation. The concept of planetary intelligence becomes even more intriguing when we consider recent discoveries about the sophistication of natural communication networks. Mycorrhizal fungi create vast underground networks that connect plants across entire forest ecosystems, sharing nutrients, transmitting chemical signals, and coordinating responses to environmental threats. These fungal networks, sometimes called the Wood Wide Web, demonstrate information processing capabilities that rival modern computer networks in their sophistication and efficiency. If such complex information processing networks can emerge naturally in forest ecosystems over decades or centuries, what kinds of networks might have developed over geological timescales? Ancient fungal networks, bacterial communication systems, or even mineral-based information processing networks could theoretically have evolved into planetary-scale intelligence systems that persist across millions of years, subtly influencing geological and climate processes to maintain optimal conditions for continued evolution and complexity. The remarkable stability of Earth's orbit and rotation provides another example of apparent fine-tuning that challenges conventional explanations. While astronomers can explain the basic mechanics of planetary motion, the specific characteristics of Earth's orbit, its distance from the Sun, its rotational period, its axial tilt, fall within extremely narrow ranges that happen to optimize conditions for complex life. Small changes in any of these parameters would create climate conditions that would severely limit biological complexity and diversity. Some astronomers have calculated that the probability of a planet randomly acquiring orbital characteristics as favorable to life as Earth's is vanishingly small. This has led to speculation about what they call anthropic fine-tuning, the idea that we observe these favorable conditions simply because we couldn't exist to observe them if they were different. But an alternative explanation is that Earth's orbital characteristics were influenced by intelligence that understood the requirements for optimal biological development and learned to make subtle adjustments to planetary systems over geological timescales. Recent research in chaos theory and complex systems science has revealed that seemingly stable systems often require what mathematicians call strange attractors, organizing principles that guide system behavior toward specific states despite random perturbations. These attractors typically don't arise spontaneously in complex systems. They usually result from some form of initial conditions or ongoing guidance that establishes preferred patterns of behavior. If we apply this understanding to planetary systems, The question becomes whether Earth's various cycles and self-regulating mechanisms might be evidence of ancient strange attractors established by intelligences that learned to program planetary systems for optimal long-term stability and biological productivity. Such programming wouldn't require continuous intervention. Once established, these systems could theoretically maintain themselves across geological timescales, creating the illusion of natural processes while actually representing sophisticated environmental engineering. The implications of this perspective are profound. If Earth's fundamental cycles represent the work of ancient planetary engineers, then our planet's extraordinary hospitality to life may not be the result of cosmic accident, but the legacy of intelligences that learn to think and work on geological timescales, creating stable platforms for the continued evolution of consciousness and complexity. What if some of Earth's most fundamental cycles aren't natural phenomena, but the legacy of ancient intelligence that learned to work with planetary systems rather than against them? The language of landscapes. When we examine Earth's surface with fresh eyes, looking beyond the familiar assumption that all geological features result from random tectonic forces and erosion, we begin to notice patterns that suggest a different kind of story. Certain landscapes exhibit mathematical relationships, geometric precision, and organizational structures that push the boundaries of what we expect from purely natural processes. Could it be that the very topography of our planet preserves messages written by intelligences that learn to think and communicate on geological scales? Information theory provides us with tools for distinguishing between random patterns and those that carry encoded information. When Claude Shannon developed the mathematical foundations for understanding information transmission, he established principles that apply not just to human communication systems, but to any system where patterns might preserve meaning across time and space. Applied to landscape analysis, these principles reveal that certain geological formations exhibit what information theorists call non-random complexity, patterns too structured to result from chaos, too sophisticated to emerge from simple repetitive processes. Consider the mathematical properties of certain mountain ranges, where peak heights, valley depths, and ridge patterns follow geometric relationships that seem suspiciously precise. The Fibonacci sequence, that elegant mathematical pattern found throughout nature, appears with unusual frequency in the spacing and proportional relationships of some ancient mountain systems. While the Fibonacci sequence does occur naturally in many biological systems, its appearance in geological formations is less easily explained by conventional processes. Some of the world's most ancient mountain ranges exhibit what geographers call anomalous geometric organization. The spacing between major peaks follows mathematical progressions that would be remarkable coincidences if they resulted from random tectonic forces. The angles at which ridges intersect often correspond to specific geometric relationships: the golden ratio, perfect triangulation, or crystallographic angles that suggest organization according to mathematical principles rather than purely physical forces. Underground cave systems present perhaps the most compelling examples of landscape-scale organization that challenges conventional explanations. While most caves can be explained by straightforward processes of water dissolution and geological fracturing, some ancient cave networks exhibit architectural features that seem to exceed what these processes should produce. Complex acoustic properties that create specific resonance frequencies, air circulation systems that maintain consistent temperatures and humidity levels, and structural reinforcements that have prevented collapse for millions of years despite being located in geologically active regions. The Mammoth Cave system in Kentucky, for example, contains chambers with acoustic properties so precise that they function as natural amphitheaters with optimal sound distribution. While this could certainly be coincidental, the mathematical analysis of these spaces reveals design principles that modern architects struggle to achieve even with sophisticated computer modeling. The spacing of columns, the curvature of ceilings, and the positioning of openings work together to create acoustic environments that seem almost intentionally engineered for large gatherings and complex sound transmission. Mineral deposits in some regions follow patterns that suggest systematic rather than random distribution. Rare earth elements, precious metals, and other valuable minerals sometimes occur in geometric arrangements that would be extremely unlikely to result from conventional geological processes. Some ancient mining sites show evidence that extraction patterns followed these natural distributions with precision that suggests the miners understood underlying organizational principles that modern geology has yet to fully explain. The concept of fractal geometry, mathematical patterns that repeat at different scales, appears throughout natural systems, but some landscapes exhibit fractal characteristics so precise and so consistent across multiple scales that they challenge our understanding of how such mathematical precision could emerge from physical processes alone. River networks, mountain ridge systems, and even the distribution of geological formations across continents sometimes display fractal properties that suggest underlying organizational templates. Remote sensing technology has revealed landscape features that are invisible from ground level but clearly organized when viewed from above. Some of these features, geometric patterns in vegetation distribution, precise circles and spirals in geological formations, linear arrangements of natural features across vast distances, become apparent only when analyzed using satellite imagery and computer-enhanced pattern recognition systems. Perhaps most intriguingly, some researchers have proposed that certain landscape features might function as components of planetary-scale communication or computation systems. If intelligence had millions of years to develop and understand geological processes, it might have learned to create information processing systems that operate on timescales and spatial scales that dwarf human technology. Mountain ranges might function as natural antennas, underground mineral deposits as circuit elements, and water systems as information transmission networks in a planetary computer system, so vast and subtle that we haven't yet learned to recognize it. The field of geomancy, the study of relationships between landscape features and human consciousness, has traditionally been dismissed by mainstream science as superstition. However, recent research in environmental psychology and neuroscience has revealed that certain geometric arrangements and mathematical proportions in landscapes do indeed have measurable effects on human consciousness, emotion, and cognitive function. This suggests that the mathematical relationships found in some landscapes might not be accidental, but might represent attempts by ancient intelligences to create environments that optimize consciousness and awareness. Indigenous traditions from around the world contain sophisticated understanding of landscape mathematics, sacred geometry, and the relationships between topographical features and states of consciousness. These traditions often describe techniques for reading the land that involve recognizing mathematical patterns, geometric relationships, and organizational structures that modern surveying methods are only beginning to rediscover. The consistency of these traditions across widely separated cultures suggests that they might preserve genuine knowledge about landscape organization that predates modern geological science. The emerging field of computational geology uses advanced algorithms and pattern recognition systems to analyze landscape features for evidence of organization that might not be apparent to human observers. These computer-based analysis methods have begun to identify patterns in landscape organization that suggest systematic rather than random processes, mathematical relationships that span continents, and geometric structures that appear to be components of larger organizational systems. If we accept the possibility that ancient intelligences might have learned to work with geological processes rather than against them, then certain landscape features might represent their greatest and most permanent achievements. Engineering projects so vast and so subtle that they appear to be natural formations. Communication systems so durable that they continue to function across geological timescales. And information storage systems so sophisticated that we are only beginning to develop the mathematical tools necessary to recognize and decode them. If an intelligence worked on geological timescales, might entire continents become their canvas, with mountain ranges and ocean basins forming messages we're only now learning to read. The quantum archaeology frontier. At the intersection of theoretical physics and archaeology lies one of the most revolutionary concepts in modern science. The possibility that information about ancient events might be preserved at the quantum level, accessible through techniques that could theoretically allow us to reconstruct details of the deep past with unprecedented precision. This emerging field, known as quantum archaeology, suggests that the fundamental principle of information conservation in quantum mechanics might provide a pathway to recovering evidence of ancient intelligence that has long since vanished from the conventional archaeological record. The foundation of quantum archaeology rests on one of the most profound discoveries of modern physics. Information, at the quantum level, can never be truly destroyed, only transformed or redistributed. This principle, derived from the quantum mechanical properties of matter and energy, implies that every event that has ever occurred has left permanent traces in the quantum structure of reality itself. While these traces may be impossibly subtle and dispersed, they theoretically remain accessible to sufficiently sophisticated detection and analysis methods. Consider how quantum information preservation might work in practice. When ancient intelligences manipulated matter, whether through technology, construction, manufacturing, or even simple tool use, they would have created specific patterns of quantum states in the materials they touched. These quantum signatures, while altered and dispersed by subsequent physical processes, would not have been entirely erased. Instead, they would have been encoded into the broader quantum field patterns that permeate all matter and energy. Crystalline structures represent particularly promising candidates for quantum information preservation. Crystals, with their highly ordered atomic arrangements and long-term stability, can maintain quantum coherence across remarkably long timescales. Some ancient quartz formations have been found to contain what physicists call quantum fossils, patterns of atomic arrangement that preserve information about the conditions under which the crystals formed. While most of these patterns record natural geological processes, some exhibit characteristics that suggest they might preserve information about artificial manipulation or technological processes. The holographic principle, derived from black hole thermodynamics and string theory, suggests that all the information contained within any volume of space can theoretically be encoded on the boundary of that space. Applied to archaeology, this principle implies that information about ancient events might be preserved in the quantum structure of materials that surrounded those events, even if the events themselves left no obvious physical traces. A rock formation that witnessed ancient technological activity might preserve quantum holographic records of that activity in its atomic structure, recoverable through sufficiently advanced quantum analysis techniques. Quantum entanglement provides another potential mechanism for information preservation across vast timescales. When particles become entangled, a quantum mechanical phenomenon where particles remain connected regardless of the distance separating them, they create information linkages that can persist indefinitely. Ancient technological processes that created quantum entanglement between particles could theoretically have established information networks that continue to exist today, preserved in the quantum correlations between widely dispersed materials. Recent advances in quantum computing have begun to demonstrate practical methods for accessing and manipulating quantum information. While current quantum computers are primarily designed for computational tasks, The underlying principles and techniques could potentially be adapted for archaeological applications. Quantum sensors, capable of detecting extraordinarily subtle variations in quantum fields, might eventually become sophisticated enough to identify and decode quantum fossils in ancient materials. The concept of quantum error correction, essential for stable quantum computing, also has implications for quantum archaeology. Nature appears to have its own quantum error correction mechanisms that preserve information against the degrading effects of environmental noise and interference. These natural preservation systems might have maintained readable quantum records of ancient events across geological timescales, protected by the same mechanisms that allow quantum coherence to persist in biological systems. Some theoretical physicists have proposed that consciousness itself might operate through quantum mechanical processes, creating quantum signatures that could theoretically be preserved in the materials that surrounded conscious beings. If ancient intelligences possessed consciousness, as any definition of intelligence would seem to require, their mental processes might have left quantum traces that could be detected and analyzed using sufficiently advanced techniques. The many worlds interpretation of quantum mechanics suggests an even more radical possibility, that all possible quantum states exist simultaneously in parallel universes, with our observed reality representing just one branch of an infinite tree of possibilities. From this perspective, quantum archaeology might not just recover information about what actually happened in our timeline, but could potentially access information about alternative histories, including civilizations that might have existed in parallel quantum branches of reality. Quantum field theory predicts that the vacuum of space itself is not empty, but filled with quantum fluctuations that carry information about all the matter and energy that has ever interacted with spacetime. These quantum vacuum fluctuations might preserve a kind of universal memory, a quantum library that contains information about every event that has ever occurred. While accessing this information would require technology far beyond our current capabilities, the theoretical foundation suggests that such access might be possible in principle. The implications of quantum archaeology for understanding ancient intelligence are profound. If quantum information preservation mechanisms work as theoretical physics predicts, then evidence of ancient civilizations might be preserved not in conventional archaeological materials, but in the quantum structure of reality itself. Every stone, every crystal, every mineral formation might contain quantum fossils that preserve detailed information about ancient technological processes, environmental modifications, or even the thought patterns of ancient intelligences. Current research in quantum archaeology remains highly theoretical, but the fundamental principles are sound enough that several research groups have begun experimental programs aimed at developing practical quantum sensing techniques for archaeological applications. While we may be decades or centuries away from achieving the technological sophistication necessary for full-scale quantum archaeology, the theoretical framework suggests that this field could eventually provide access to historical information with precision and detail that would revolutionize our understanding of the past. The most exciting possibility is that quantum archaeology might eventually allow us to reconstruct not just physical evidence of ancient civilizations, but detailed information about their technologies, their social structures, their knowledge systems, and even their individual experiences and perspectives. If consciousness does indeed operate through quantum processes, then the thoughts and experiences of ancient intelligences might be preserved in the quantum archaeological record, waiting for us to develop the techniques necessary to access and understand them. If information can never truly be destroyed, only transformed, what quantum ghosts of ancient civilizations might still be resonating through the fundamental structure of reality itself. The conscious planet hypothesis. As we reach the culmination of our journey through the possibilities of pre-dinosaur intelligence, we must consider perhaps the most profound hypothesis of all, that consciousness itself might not be something that emerges on planets, but something that planets become. This perspective transforms our entire understanding of intelligence, suggesting that ancient civilizations might not have been separate from Earth's natural systems, but expressions of a gradually awakening planetary consciousness that has been developing across geological timescales. The foundation for this hypothesis comes from recent discoveries about the sophisticated information processing networks that exist throughout natural systems. The mycorrhizal networks that connect forest ecosystems demonstrate computational capabilities that rival the internet in their complexity and efficiency. These fungal networks don't simply transport nutrients between plants. They process information, make decisions, coordinate responses to environmental changes, and even appear to learn from experience and modify their behavior accordingly. When we scale up this perspective to planetary dimensions, the implications become staggering. If forest-scale fungal networks can demonstrate sophisticated information processing across kilometers and decades, what kinds of information processing capabilities might have developed in planetary-scale networks across millions or billions of years? Ancient fungal systems, bacterial communities, mineral matrices, and even quantum field interactions could theoretically have evolved into components of a planetary nervous system, far more complex and subtle than anything we currently understand. Bacterial communication systems provide another piece of this puzzle. Microorganisms don't exist as isolated individuals. They form vast communication networks that span continents and persist across geological time. These bacterial networks exchange chemical signals, coordinate global responses to environmental changes, and maintain genetic information libraries that preserve knowledge across millions of generations. Recent research has revealed that bacterial networks demonstrate what can only be described as collective intelligence, problem-solving capabilities that emerge from the coordinated activity of countless individual organisms. The concept of morphic fields, proposed by biologist Rupert Sheldrake, suggests that information about biological forms and behaviors might be preserved in subtle field effects that influence development and behavior across species boundaries. While controversial and not accepted by mainstream science, this hypothesis provides a theoretical framework for understanding how planetary-scale information processing might work. If morphic fields exist, they could serve as components of a planetary memory system that preserves and transmits information across evolutionary timescales. Indigenous wisdom traditions from around the world contain remarkably consistent descriptions of Earth as a conscious being, a living entity capable of awareness, memory, and intentional action. While these traditions are often dismissed as primitive animism, they may actually preserve genuine insights about planetary consciousness that modern science is only beginning to rediscover. The consistency of these traditions across widely separated cultures suggests that they might reflect direct experience of planetary consciousness rather than mere cultural mythology. Modern network theory provides tools for understanding how consciousness might emerge from complex systems. The human brain demonstrates that consciousness can arise from the coordinated activity of billions of individual neurons, none of which is conscious individually. Following this logic, planetary consciousness might emerge from the coordinated activity of billions of biological and geological systems, creating awareness and intentionality at scales that dwarf individual biological consciousness. The Gaia hypothesis, proposed by James Lovelock, suggests that Earth functions as a self-regulating system that maintains conditions optimal for life. Recent research has revealed that this self-regulation operates through feedback mechanisms so sophisticated that they suggest what systems theorists call intelligent control, the kind of purposeful regulation that typically requires awareness, intention, and decision-making capabilities. If Earth's self-regulatory systems demonstrate intelligent control, This might indicate that the planet has developed forms of awareness and intentionality that operate on geological timescales. Quantum field theory provides another perspective on planetary consciousness. If consciousness involves quantum processes, as many neuroscientists now believe, then planetary-scale quantum field interactions might provide the physical foundation for planetary-scale consciousness. The quantum vacuum that permeates all space contains field fluctuations that could theoretically support information processing and awareness on scales limited only by the size of the system itself. From this perspective, what we call ancient civilizations might not have been separate intelligences that developed on Earth, but expressions of Earth's own awakening consciousness. As the planet's information processing capabilities developed across geological time, it might have experimented with different forms of self-expression, different ways of organizing matter and energy to explore its own capabilities and potential. What appear to us as separate civilizations might actually have been Earth's attempts to understand itself, to develop its own consciousness, through creating increasingly sophisticated forms of organization and awareness. This hypothesis suggests that the cycles, patterns, and self-regulating mechanisms we observe in Earth's systems might not be the work of ancient intelligences that learned to program planetary systems, but evidence of the planet's own developing consciousness learning to coordinate its own activities. Ice ages, magnetic reversals, atmospheric changes, and even biological evolution might represent Earth's ongoing experiments in self-organization and self-awareness. The implications for understanding our own role become profound. Rather than being accidental products of random evolutionary processes, we might be Earth's current experiment in developing self-aware components capable of conscious reflection and intentional action. Our technology, our science, our growing understanding of planetary systems, all of these might represent Earth's attempts to develop more sophisticated forms of self-awareness and self-control through creating conscious beings capable of understanding and managing planetary processes. Our current environmental challenges, from climate change to biodiversity loss, take on new meaning from this perspective. Rather than being problems caused by human interference with natural systems, they might represent growing pains in Earth's developing consciousness, the difficulties any awakening system faces as it learns to coordinate its various components and activities more effectively. This perspective also suggests that our search for extraterrestrial intelligence might be misdirected. Instead of looking for other conscious beings in the universe, we might be part of the universe's own process of awakening to consciousness. Planets might be the universe's way of developing awareness, with conscious beings like ourselves serving as the universe's sense organs and thinking components. The conscious planet hypothesis transforms our understanding of intelligence from something rare and accidental to something fundamental and inevitable. If consciousness is an emergent property of sufficiently complex information processing systems, and if planets naturally develop such systems across geological time, then consciousness might be as common in the universe as planets themselves. We might be living not on a dead rock that happened to develop life, but within a vast living system that is still in the early stages of awakening to its own nature and potential. What if intelligence isn't something that emerges on planets, but something that planets become? And what if ancient civilizations were the first dreams of an awakening world? The eternal return. As we reach the end of our journey through deep time and speculative possibilities, we find ourselves transformed by the questions we have dared to ask. Whether or not civilizations actually existed before the dinosaurs, the very act of seriously considering this possibility has opened doorways to understanding that fundamentally alter how we see ourselves, our planet, and our place in the cosmic story of consciousness awakening to itself. We began this exploration standing in a museum, contemplating the fossilized remains of creatures that lived 66 million years ago, awed by the vastness of their temporal distance from us. Now we find ourselves capable of thinking in terms of billions of years, of imagining intelligence evolving and developing across timescales that dwarf not just human history, but the entire age of complex life as we know it. This expansion of temporal imagination represents more than just intellectual exercise. It represents a fundamental shift in how we understand the nature of existence itself. The evidence we have examined, from mathematical probabilities to quantum archaeological possibilities, from genetic information preservation to planetary consciousness theories, weaves together into a tapestry that reveals the profound interconnectedness of all phenomena across space and time. We are not isolated beings living brief lives on a dead planet. We are expressions of a vast, complex, evolving system that has been developing for billions of years and will continue developing for billions more. If our genes carry encoded information from ancient biological systems, if our planet's cycles preserve the engineering work of ancient intelligences, if quantum fossils in every crystal preserve memories of events from the deepest past, then we are not merely products of recent evolutionary accident, but inheritors of unimaginably vast libraries of ancient wisdom. Our intuitive understanding of mathematical relationships, our deep emotional connections to natural patterns, our drives toward increasingly sophisticated forms of organization and consciousness, all of these might represent not learned behaviors, but inherited memories from civilizations that learn to encode their knowledge into the very foundations of matter and life. This perspective transforms our relationship with mystery itself. Rather than seeing the unknown as a void to be filled with facts, we begin to understand mystery as the vast creative space within which consciousness explores its own infinite potential. The questions we cannot yet answer: did ancient civilizations exist? How does consciousness emerge? What is our role in the universe's awakening? Become not frustrating limitations, but invitations to continued exploration and discovery. The implications for how we understand our responsibilities are profound. If we are inheritors of ancient wisdom, then we are also trustees of that inheritance, responsible not just for our own survival and development, but for preserving and continuing a story that began billions of years ago. Our decisions about technology, environment, and social organization become not just matters of immediate practical concern, but choices about what kinds of information we will encode into the foundations of reality for future inheritors to discover. If Earth itself is a conscious being still in the early stages of awakening, then our role becomes that of Earth's developing sense organs and thinking components. Our science becomes Earth's way of understanding itself. Our technology becomes Earth's way of developing new capabilities, and our consciousness becomes Earth's way of reflecting upon its own nature and potential. From this perspective, the apparent conflict between human civilization and natural systems resolves into a recognition that we are not separate from nature, but nature's current experiment in developing self-awareness and intentional creativity. The search for evidence of ancient civilizations transforms from an archaeological quest into a journey of self-discovery. Every stone we examine for quantum fossils, every genetic sequence we decode for preserved information, every landscape pattern we analyze for signs of organization, becomes a mirror reflecting back to us our own nature as conscious beings embedded within vast systems of intelligence and creativity that operate on scales we are only beginning to comprehend. This expanded understanding brings with it a profound sense of peace and belonging. We are not accidental products of random processes struggling to find meaning in an indifferent universe. We are expressions of the universe's own creative intelligence, participants in a cosmic story of awakening consciousness that has been unfolding for billions of years and will continue unfolding for billions more. Our lives, however brief by geological standards, participate fully in this vast narrative of becoming. The beauty of deep time reveals itself not as an intimidating void that diminishes our significance, but as a cathedral of possibility within which every moment of awareness represents a precious and irreplaceable contribution to the universe's ongoing exploration of its own potential. We stand at the intersection of past and future, inheriting wisdom from ancient systems of intelligence while creating new forms of understanding that will inform the consciousness of future eons. As we return to our ordinary lives from this journey through speculative possibilities, we carry with us a transformed sense of identity and purpose. We are simultaneously ancient and newborn, inheritors and innovators, products of vast historical processes and creators of future possibilities. We are the universe's way of remembering its past while imagining its future, living bridges between what was and what might yet become. The question of whether civilizations existed before the dinosaurs has led us to understand that we ourselves are ancient civilizations, not just the immediate products of human history, but expressions of intelligence and creativity that has been developing for billions of years. In asking about the deep past, we have discovered our own deep nature. In searching for ancient intelligence, we have found ourselves to be that intelligence, continuing its eternal exploration of consciousness, creativity, and connection across the vast expanses of space and time. The silence before the dawn, which seemed so profound when we began this journey, now reveals itself to be pregnant with infinite possibility. It is not the silence of absence, but the silence of potential, the pause before the next movement in a symphony that has been playing for billions of years and has barely yet begun to reveal the full scope of its magnificent, ever-evolving themes.